All right, so now we're going to move on to Unit 2, which is actually Chapter 4, and that's going to be dealing with quadratic equations. Now, Chapter 3, or what we called Unit 1, is directly tied to quadratic equations because quadratic functions was how do we look at quadratic functions and what does that mean on a graph and how do we shift that graph using a bunch of transformations. And we dealt with solving for the actual equations and then manipulating them into general form. Now what we're going to do is just expand upon that and say, well, in quadratic equations, we're looking for specific solutions in specific moments, often what we're going to call our root zeros or x-intercepts. And we'll do some further analysis on this, but this is again going to go into some portions on our graphing calculator, which is actually where we start with lesson 4.1. And then when we move forward, we might do our algebraic methods, which we actually covered in our chapter 0 or unit 0, which was factoring. And you're going to see lots of repetition from that. So as we move forward, I think you're going to recognize a lot of this material we're doing. For now, we're going to start with dealing with quadratic equations, what that means, and then how do we solve these things on our graphs or graphing calculators. Now, recall the following. From our previous unit, we said that the general form of a quadratic function is, well, we want to write it as f of x, which was equal to y, which is equal to ax squared plus bx plus c. And this is actually directly below in the below statement where we talk about quadratic equations versus the functions, but functions are always defined generally in terms of this f of x, where x is our input, which is equal to y, which is our output, which is equal to the ax squared plus bx plus c, which this is a degree 2 polynomial. Now, where we take this into quadratic equations is we say, well, if we take this second degree equation, second degree meaning it had a degree 2 from our leading coefficient here, or our leading term, I should say, then what we're going to do is we're going to say, if we take this form, our general equation, and set it equal to 0, where our x squared coefficient cannot equal 0, or else this would become a linear term, we're going to say that we could get an example that's like this, and we set it equal to 0 for a very specific reason. When we set it equal to 0, we're saying essentially that the y value is equal to 0. And when y is equal to 0, just like we've talked about in Math 10C and previous sections, we say that this would be an x-intercept. Now that leads us into these pieces of terminology, roots of an equation and zeros of a function. The zeros, or let's first talk about the roots of an equation are the solutions. So if you ever hear, what are the solutions to this equation? They're asking for the roots of the equation. And you can find these by factoring, and then these are determined as the x-intercepts of the graph. Similarly, if I ask for the zeros of a function, well, these are the values for which f of x is 0. Again, what is f of x? F of x is just a fancy way of saying the y value is 0, or that our input or output value is 0, so we're on the x-axis, and therefore any x values we get from this are going to be the x-intercepts of the given function f of x. So just treat these things as very similar, and you can actually highlight this as like one thing, two things, and then what we could do off to the side here and what we did in class is we said, let's just throw like x-intercepts right here. Because if we throw x-intercepts here, and I'm going to try and just write that a touch neater here, if we write x-intercepts, it will help us tie both of these together here. Perfect. And you could even draw an arrow to this and an arrow to our zeros, indicating that these mean the exact same thing here. Perfect. Okay, now let's just do a quick review on taking a graph, writing the vertex form and general form based on a graph. So this came from our previous unit, and we saw that when we were given a graph, there was one thing that was always missing from the equation in vertex form. Let's actually just write out our equation in vertex form. It's y is equal to a in brackets x minus the p-value, which is the vertex value of x, squared, plus q, which was the y value of the vertex. Now, we were always missing this a value, so let's just take a second to identify what the a value is before we get our equation. I'm going to go down to the vertex. The vertex is right here. This looks to be at 1 and -9. Perfect. And I'll make sure just to erase that. There we go. 1 and -9. Now we just need to pick another point. I'm going to pick maybe the one up here, which is one of our x-intercepts. We see this as -2 and 0. So as long as you have 2 points, realistically, we can even have used this one, which is at 1, 2, 3, 4. So this would be at 4 and 0. If you want to use that x-intercept as your x or y, that would also be okay. And just to be more specific, I'm going to label these. So here's my xy, here's an xy, and then here is a p, and here is our q. Awesome. So now we're just going to choose whichever one we want from here, and that'll be fine. I'll even put a dot at our x-intercept here. Okay, The points that I'm going to use -2 and 0, and I'm going to use 1 and -9, because we have to use our vertex, but we need one of these x and y points. So we go back up here and we say, well, y was equal to 0, which is equal to a, which is the value we're trying to solve for. Our x was -2. The p-value was +1, meaning we actually put a -1 in our brackets. We always put the opposite for p. And then plus q, well, q was -9. Okay, this is going to be 0 is equal to a. -2 minus 1 is -3. -3 squared will give us 9, but let's just show this precursor step there. So this will be a 9 minus 9. When we move the 9 across, we're going to go +9 plus 9. This will give us the following. We're going to get 9 is equal to a times 9. And if we divide both sides by 9, therefore the a value is equal to 1. Now, again, some of you from our previous unit might have been like, wait a minute, if we get an a value of 1, does that really cause a stretch factor? No, not really, because it just keeps the original graph intact in terms of the stretch factor or the vertical stretch factor about the x-axis, but we still always need to solve for it because we're never 100% sure. Now, this gives us our first equation. Therefore, we have y, which is equal to, realistically, if a is 1, we don't really need to put it, x minus 1, which was our vertex value, minus 9, which was our q value. Awesome. So we're going to highlight this piece because this is one of our answers for the system here, or not the system, but for one of the equations. This is our vertex form. Now, in order to get general form, we're just going to take this a step further and say, well, what if I need to make this into general? I'm going to expand this. So we know a binomial squared must be written out twice. We don't want to just square both the terms, x squared and minus 1 squared. That wouldn't make sense. So we're going to expand this. Now, when I distribute the terms, I'm going to get y is equal to, for the first one, it's going to be x squared, then it's going to be -1x, then another -1x, -1 times 1 is +1, minus the 9 that was already there, and therefore, if I collect my constant terms together, and then I collect my x terms together, I'm going to get x squared minus 2x, and then 1 minus 9 gives us -8. There we go. This is our term in terms of, or our equation in terms of general form. So now we have the two together here. And what I'm going to do is, just to make this a little bit clear, we took our answer and brought it down here to continue this. Perfect. There we go. Okay. Now, what are the values or the x values of the function when y equals 0? What are these values? Well, the values of these are going to be our x-intercepts. So if you look over on the graph here, we had 2 points where y was equal to 0. And what are those x values? X equals -2, x equals 4. Those were the x-intercepts. And so we're going to go over here, and we're going to go to here and say that we have x is equal to -2, and then x is equal to +4. Now, realistically, you could just go -2, 4. That would be okay, but that's perfect. Can you write in a quadratic equation that has the roots of the same values of x? In fact, yes, we can. Here's what it looks like. And you're going to have no real expectation to carry this form forward, but it is a useful form. From Math 10c, we learned that we can write these functions of f of x, which is also equal to y, in terms of these roots. Well, the roots, or the x-intercepts, are -2 and 4. When we plug them in, it's going to be the following: x minus 2 times x plus 4, or minus 4. And I'm just going to make sure this one is actually a plus. The reason is because whatever our answer becomes, -2 and +4, in future lessons, you're going to see when we put them into the equation or back into the roots of the equation, you're going to find that it actually becomes the opposite. Similarly, when we talked about the p-value, we said whatever the p-value was on the graph, it was always opposite of what you saw in the brackets. So for this one, if it's -2, it's actually +2. If it's +4, it's actually -4. And if you don't believe me, take this and expand it out, and you'll see you actually get the exact same form in that general form right there above. All right, now let's go into the key ideas revolving around the graphs and the different types of solutions that are possible for this. So in this unit, you're going to see that if we take any sort of form, which is general form or vertex form, and we plot it on a graph, the ax squared plus bx plus c equals 0, where 0 is equal to the y value, aka we're solving for the x values or the x-intercepts, then the solutions or the x-intercepts can be the following. We can either have 0 solutions, 1 solution, or 2 real 0 solutions, or basically just 2 solutions. Okay, let's look at the first case scenario. If I have 0 solutions, here's what the graphs could look like. I could have a graph that looks like the following. It swoops up like this, and I could draw its tails on the end like this. You look at this and you would say, well, it doesn't ever cross the x-axis. In fact, if this is the x-axis, we can clearly see the gap right there. So that's one example where there's 0 solutions. The other one would be where it faces down like this. If it's reflected downwards or there's a vertical reflection about the x-axis, this also doesn't cross the x-axis. That red line, I never see the blue line cross it, so therefore that's 0 solutions. All right, we're going to go to 1 solution. Before we get to 2, we want to go to 1. I'm going to make this a red graph to differentiate it just a little. And I'm going to draw it kind of very similarly. So there we go. And I don't want to make sure it's a v. That's kind of more of an absolute function. We want to draw it more like a parabola. It's being a little stubborn there. Let's see. Okay, I'm just going to freehand this. Okay, so we come down. We touch the x-axis one time. There it is. Here's our arrows up. Now, we want to put a dot here to show that this crosses exactly one time. At this inflection point, we see that it is exactly one time, or at the minimum value if we wanted to call it that. Now on the other side, what I'm going to do is just show the reflection about the y-axis, or about the x-axis, I should say, because it's a vertical reflection. And again, this is going to have one x-intercept, because if we drew a line on our x-axis here, you're going to see that it crosses once here. And then if it was the upwards graph or the upward reflected graph, we would see this crossing one time here. Okay, so that's one time. Now we're going to go to our if it crosses 2 times. If it crosses 2 times, here's what the graph is going to look like. It is going to swoop right below the x-axis and come right back up. So we have that minimum, and the minimum is below the x-axis, and then we get these 2 crossover points, so 1 and 2. Now, if there was a vertical reflection about the x-axis, we could draw our graph like this, where it swoops above the x-axis and comes back down. Here's our tails on the end, representing that it goes to infinity. And then we have 1 crossing and 2 crossings. There is an example, again, of 2 real zeros, or 2 x-intercepts. So these are the 3 situations we're going to deal with in a ton. And in fact, our next example, you're going to see one equation from each of these types, just to further emphasize that these are our 3 options. And then don't be surprised if you land in one of these categories. And again, we're not saying that like these graphs are in combination, so it's 1 x-intercept, 2 x-intercept. These are all independent cases. So if I have this, this, and this, they're all independent. If I have all my downward reflected graphs, these are independent as well. Okay, now let's flip the page here, and we're going to look at these graphically. So you're going to need your graphing calculator, and I'm going to bring up my graphing calculator here on the screen in just a second. But first, what we want to do is they're going to ask us, given these 3 equations at the top, what we want to do is make them into function form. Now, the only thing we're going to change is this is equal to 0, equals 0, equals 0, because when it's set equal to 0, this gives us some sort of equation. When we want the function, we just convert it back to f of x to describe the entire graph. So we're going to write f of x is equal to negative x squared plus 6x minus 9. For the next one, same thing. F of x is equal to negative x squared minus 12x minus 35. There we go. And then our next one, or our third one, is going to be f of x is equal to x squared minus 10x and then plus 30. There we go. Now let's just take a look at all the functions just to make sure they're all good. So we have negative x squared plus 6x minus 9, good. We have negative x squared minus 12 minus 35, good. And then lastly, f of x equals x squared minus 10x plus 30. We just want to make sure they're all good because all we've changed here is writing f of x instead of 0. Okay, let's go through these individually. So we're going to start off with the first one, and they're going to ask us for the graph and the window settings. Now, just remember when we talk about the window settings, before we even go to our graphing calculator, it's always the minimum value, the maximum value, and then the scale, or SCL. Now, in this specific order, we want to record them. Typically, what we're going to do, and we can fill this out before we even type this into our graphing calculator, let's try to keep the scale at 1 for most of these. I mean, you could change that, but like I think keeping the scale at 1 is generally a little bit better just because it simplifies things for us in terms of determining the window settings. Now what we're going to do is we're going to copy this function in our graphing calculator. So I'm going to bring it open here and go, well, first of all, we have negative x squared, and then we have plus 6x, and lastly, minus 9. Now just make sure if you're putting a negative value, you're putting the negative. If you're putting minus, you're putting the minus. Okay, we're going to graph it. Now, our window settings, if they look like this and they're like way off, and there's like, and you've been working with another function and now you want to get back to the original, click zoom and then go down to 6, which is zoom standard. And then you're going to want to click enter. Now, this will get us to here. There's our standard window. And now we see that our parabola is actually like kind of, it's tucked in the bottom right. So we need to adjust our window settings a little bit because we're like, we don't want a picture that just shows the entire Cartesian plane with all this null space around, which I call like the white space. We want it to be highlighting the graph. So what we see is that we're going to need to move our x-axis so that it's less negative. So I'm going to go window and make my x minimum something like -1 should be okay. So make sure you clear that out and put -1. Then we're going to graph it. Okay, this is looking a little better, but we would still do a bit better. We have a bunch of null space or white space above the x-axis. I'm going to make my window for y maximum, let's set it to something like 1. Because then what this is going to do is it's going to lower it, so now that I just see my graph. And then realistically, we can make this a touch better and say, hey, well, because there's a bunch of white space on the right of this graph, let's shrink our x max to something like maybe 8 instead. So just a couple less units. So here's what our window settings that we're going to use are the following. I'm going to go down into my x values and say my x minimum is -1, my x maximum is +8. And I'll make sure that actually kind of looks like an 8. There we go. And then for my x, or for my y minimum, I'm going to set this to -10. I'm going to set my maximum to 1. And then, of course, for both of these, the scale is going to remain at 1. So this will be good. Now let's graph this. Hey, this is what it looks like. Now, here's what we're going to do. We're going to create a rough sketch of this on our graph. Because in this little box, we're going to have to make some sort of rough sketch of this. So there we go. There's our axis points. We see that it faces downwards. So what I'm going to do is I'm going to go to my colors here. I'm going to do the graph, and let's just make sure we take another look at it. Perfect. So it crosses about here, comes up, touches, and then comes back down. And again, these are just very rough sketches, so they don't have to be extremely accurate, but enough detail where you can see stuff going on. Now, something we want to do from here is they're going to ask us for the x-intercepts. So to get the x-intercepts, here's what we can do. We can go second trace, or on the Casio's, shift G solve, 0 or x-intercept. Now it's going to ask us left and right bound. For the left, you want to be somewhere on the left-hand side of that x-intercept. So somewhere about here. Then you want to click enter. It will ask you right bound. You want to move your right cursor somewhere over here. And then lastly, when you click enter, it will ask you to guess. You want to bring it as close as possible right to that x-intercept. In this case, I get an x-intercept at this very point right here of 3 and 0. So we're going to record that. This is going to be 3 and 0 right at the top. Now, we could also record this, which was our y-intercept. This was our -9. So realistically, we could be like 0 and -9 for that point if we really wanted to. But I mean, that's just an extra piece here. Okay, we go down below. The x-intercepts are the zeros. The x-intercept was equal to +3. The solutions to the given equation were x equals 3 as well, which as a coordinate point is 3 and 0. There we go. So solutions are often given in terms of an equation of x equals 3. The x-intercepts are zeros. They're often recorded as a point as well. So we could even write this as first and foremost 3 and 0 representing the x-intercept. And then we could say x equals 3, just to put them in order of like what they're asking for. X-intercept, typically Cartesian plane, or an xy ordered pair. Solution, you'd want to write it as x equals 3. Okay, good. Now, let's go up to our second graph here. So we're going to clear out our original function, and we're going to be working with this one here. Let's pull up in the graphing calculator again. We're going to clear out the original function and now write -x squared minus 12x and then minus 35. Graph. And again, you're probably going to look at this and be like, wait a minute, I can't even see it. So we're going to go into zoom standard. On the Casio, what you can actually do is go into your window settings or shift V window. In the V window settings, if you click the button STD, which is sometimes it depends on where it is, but it will be STD. That means standard window, and it will bring you back to the regular window. Then you can make your adjustments. And if you need help with that, obviously come talk to me. So now we're going to look at this and say, well, we have a bunch of white space on the upper portion, and we also have a bunch of white space on the right-hand side. So for the window settings, first and foremost, I mean, we can keep our scale at 1. That might be the best thing. So keep our scale at 1. Now what we're going to do is go, well, if this is an x minimum of -10, that seemed okay because the graph on the left was okay, but the x maximum, I'm going to make it something like 1. So let's record that here. We have -10 and 1. And then for our y, what we're going to do is look at this and be like, well, first of all, let's see what it looks like for x. So this is us moving it to an x maximum of 1 and an x minimum of negative 10. So it seems pretty good. Now we can leave it as this, honestly, but what I'm going to do is just lower it a little bit in terms of the y values. I'm going to look at this and make it maybe like positive 5 for y instead. Okay, now if we make it positive 5 for y, let's record these here. So it's negative 10, and we have 5 for the y as the positives. There we go. Perfect. We're going to graph it. Here's what it looks like. Now, we could even do a touch better on this in terms of our x's if we really wanted to, but I'm generally happy with this. This isn't too bad. So what we're going to do is we're going to draw our Cartesian. So here it is, and then here it is. We're just kind of roughly putting what the window we see is based on this window settings. And then what I'm going to do is I'm going to create my function over top of this using the colors. So I'm going to put this away just for a second, grab my red. So it starts down here, it comes up, it crosses through, it then crosses through again, and it starts coming back down this way. This is the graph we see. And we could put arrows on the end because we know this extends. We're going to put dots here and here because these are our interest points. Now what we're going to do is our second trace intercept mode, or shift gsolve 0. So we go second trace. There we go. We're going to go down to 0, which is number 2. We're going to do left bound of this first one, click enter. Right bound of the second one, click enter, and it's going to tell us that we have a 0 at negative 7. So let's make sure we record that here on our graph. I'm going to go over here and then go, this is negative 7 and 0. Now we want to calculate the other one. So the one that's on the right-hand side, we're going to repeat the process, second trace 0 on the Casio's shift gsolve 0, which in this case on the Casio's, you can actually just click left and right, and it actually gives you the values right away. You don't even need to do this left bound, right bound. We're going to click left bound on the TIs. We're going to go a little bit right, click enter. You're going to have to guess. So you're going to have to bring your icon to like right about the point and press guess as the third solution. For my graphing calculator, it just, if I do left bound, right bound, it just tells me the value, x equals negative 5. So I'm going to write that in here. X is negative 5. Y is 0. We're going to close the bracket there. And I may actually undo this. Reason is because I want to kind of keep the Cartesian uninterrupted here. So what I'm going to do is just shift over my negative 7 and make sure my 5 fits here. So this is negative 7 and 0. This is negative 5 and 0. There we go. Now we're going to scroll down here and answer these. So they say the x-intercepts or zeros. Well, our x-intercepts are going to be at negative 7 and 0 as Cartesian planes or Cartesian points. Then this is going to be negative 5 and 0, which means that x is equal to negative 7 and negative 5. Remember, we could just use a comma. We don't have to say x equals over and over. In our solutions, well, the solutions are going to be the following. X equals 7 and, whoops, there we go, negative 7 and negative 5. And then again, we could write the Cartesian points if we wanted to again, but I mean, that's not necessary for this piece. As long as we have these in here, we are happy with this. And I'm just going to lower this a little bit in the case that we don't put in those other pieces. Okay, now we got our third example, very, very similarly. So now we've seen one intercept, two intercepts. I think we can predict what's going to happen on this one. We may not see any x-intercepts. We're going to type in this function here. So go back to your y equals, clear out the function. It's going to be x squared minus 10x and then plus 30. Now let's just make sure we type that in right. Yep, looks good. So we're going to graph it. Again, you're probably going to be like, I can't even see it. Click zoom, zoom 6 or zoom standard. Now it's going to give you the standard window settings and we can make the adjustments based on where it is. On the Casio calculator, you're going to go shift view window. You can click STD as the one of the buttons. I think it's F1, F2, F3. It's one of the earlier keys. You're going to click that and it will bring you back to here. Now we're going to try to eliminate a bunch of the white space. We see a graph where there's a bunch of left space that is white. There's a bunch of Y negatives that are also white. So we're going to reduce our window settings in terms of the X to make it, let's say, -1. That will be more than enough. We could, you know what? We could actually even make this 0. The X maximum, we're going to keep it at 10 because it looked like the X's were fine. Like as you can see here, all we've done is adjusted the X minimum and now it looks a little better. But now we want to increase our Y's because we don't see a lot of the graph still. All we see is just the bottom edge of it or the minimum. So we're going to go back to our window and increase the Y max to maybe like 30. And obviously not 1030, but 30. There we go. There's our graph. So what we're going to do is we're just going to copy these window settings into our window settings that are actually shown on our page here. So let me go here and let me make sure I get my pen here. So we're going to go with the x minimum, which was 0. We're going to go x max, which is 10, scale, which is 1. We're going to go x or y minimum, which is 10, y maximum, which is 30, and then we're going to go scale, which is 1. Okay, let's draw in our rough sketch here. So I go back to my graph. I want to sketch this in. So let's just make sure I have my proper tool here. So this is my x-axis down here. Our y-axis is actually like right along the edge because we set x equal to 0. So our x minimum to 0. So it's right about here. Now what we're going to do is sketch our graph over top of this. It kind of swoops down and then continues. So swoops down, gets to a minimum, and then continues this way. Awesome. And then arrows on the end because we want to indicate that this goes on. Now, clearly, there is no x-intercept here because look at the space. There's white space that exists between the graph and the x-axis. If this is the x-axis, the graph never crosses, so we get 0 here. Now, what we want to do is in the box below, when they ask us for x-intercepts or 0, we're just simply going to say none or does not exist. D and E means the does not exist. So if you ever see me write that, does not exist, D and E. When we say, what are the solutions to the graph? Just simply say, well, if there's no x-intercepts, there's also no solutions. And that is a totally valid graph, or a totally valid statement about this graph here, that there's just simply no solutions. All right, let's zoom out on this just so we can see it one more time. As you can see, we have one x-intercept, two x-intercepts, or zero x-intercepts. These graphs are all totally fine. The one thing you want to be aware of is that try to keep your scale on the graph as 1. I mean, like in certain problems, it might be good to like increase your scale. What the scale means is that each unit you see represents a certain amount of data. Or so like, let's say I go 1 tick to the right. Instead of it just being 1 unit, it might be, let's say I increase it to 50 for the scale. Each tick you would see would be 50 units. And it's sometimes a way to like truncate really large graphs, but for the most part, I try to keep that as 1, especially when you're first learning this, so that all you have to do is adjust your mins and maxes, and then you can get these windows. Now, this is a skill that you want to know, and your window settings might be different from the people around you. You might get something, and then the neighbor next to you might get something that's like plus or minus 5 of all of this stuff. But you want to be making sure that when you graph this, the window settings reflect an accurate picture of just the graph and not like a bunch of that white space or null space as I called it. So if you need help adjusting this and this is something you need to work with as a skill, come talk with me, or just get lots of practice out of the textbook, or just play around with your calculator a little bit. This stuff will always take a little bit of work to get used to, but once you kind of get the pattern, you'll be able to kind of play around with these window settings and really like hone in that skill of making sure you only see your graph. Okay, now I'm going to bring my calculator back over to my right-hand side before we move on. Here's our example 1 for our in-class examples. Now that we know that there can be 0, 1, or 2 solutions, let's look at this function here, or this equation. How would you solve this equation graphically? Give your correct answers to the nearest hundredth, or the second decimal place. Well, when I see a function like this, or more importantly, an equation like this, because a function would have to have some sort of definition of f of x or y, we look at this equation, and to make this into our calculators graphically, what we can do is we can take this and actually just reformat it so that it is equal to 0. So before we go into the different methods of 0 method or intersect method, we actually just used the 0 method, and here's how we did it. We're going to go down to this here, and we're just going to rewrite our equation in the following way. And I highly recommend you do this kind of in the middle space here. Instead of it being 2x squared plus x equals 2, I'm going to write it as 2x squared plus x. And then in order to get this 2 over onto the other side, we're going to subtract it away. When we subtract the 2 from both sides, here's what this new equation becomes. Minus 2 is equal to 0. Now we can do our different methods here. For the first one, the 0 method, we're going to write this as 2x squared plus x minus 2 is equal to 0. Now in your graphing calculators, here's what you're going to do. On the first part here, or this part of the equation, the left-hand side, I want you to type this into your y1. So it's going to be y1 is equal to all of the stuff that's above here. Now, writing out the steps here, when we calculate this in our calculator, you're going to go second, for my TI users, second, trace, and 0, which is number 2. Then what you'll be able to do is calculate your left and right bounds. So let's do that together here. We're going to go clear that function out. We're going to go our 2x squared plus x minus 2. We're going to graph it. Again, your graph might be way off. So what we're going to go is zoom and zoom standard, or on the Casio, we're going to do shift, V window, and then STD, or standard window settings. And now what we're going to do is, I like this graph generally, but like if I want to zoom it in a little bit so I can get those x-intercepts, let's, instead of adjusting our window settings, what we could do is just simply zoom in. And if we zoom in, this might actually give us the ability to see the graph without having to adjust the window settings. Now on the TI calculators, you might have to like put your icon kind of in the middle of the graph and click enter, which will then zoom it into the middle of this. On the Casios, you also have the zoom function as well, and you have the ability to just generally move left and right using your arrow keys, or up and down for that matter. So we look at this, and same thing with this one. We're going to go for our Casios, before we talk about the shift trace, we're going to go, or before we actually calculate it, I want to go shift G solve, and then we're going to click xint, or for some models 0 as well. So it really depends, because different versions have different keys in these cases, but we either have the first set of instructions or the second instructions if you have the Casio. Now let's do this in the TI. Second trace, we're going to go to our 0. We're going to go left bound, which puts us on the left hand side of the left x-intercept. We're going to go to the right hand side, click enter, and it gives us a 0 of negative 1.28. So we're going to go down here, and I'm just going to flick that out of the way. To do decimal places, we get x-intercept. We have one x-intercept where it's equal to negative 1.28. And then we also have another x-intercept. Let's see if we go over here. Second trace, 0, or shift G solve x-intercept. I'm going to go to the left of this, to the right, click enter, and I get 0.78. So positive 0.78. And again, you could write it as x equals negative 1.28, x equals 0.78, or you could just leave it like this, and this would be totally fine. Okay, we're going to highlight this because that's our solution for this. Now, using the intersect method, it's actually really similar. So we're not really going to do much different. And just to keep this a little organized, I'm going to lift this up just a tad there. There we go, and place it kind of somewhere in the middle. There we go. Our intersect method is actually going to do the same thing, and we're actually going to get the same solution. So don't be surprised if the answers are the same. What we're going to do is the following. I'm going to take this exact same way we wrote this equation here and here, and I'm just going to write it again, but I'm going to encourage you to do something in your graphing calculator that is actually fairly nice for these. So we're going to write it as 2x squared plus x minus 2 is equal to 0. Now, in your graphing calculators, we already have this one entered into y1. So this isn't going to be much different. y1 is equal to the stuff above. Now, here's where things are different. We're going to type this in for our second method, or the intersection method. This goes into y2, your 0. Now, if this is at 0, whoops, and I don't want to undo too much there. There we go. So if this goes into our second function, or y2 is 0, here's what that's going to look like. On the Casio and the TI, go back into your graph mode, go down to y2, and click 0 into y2. Now, what this actually does is, because not all of you have the graphing calculators that have color, what this does is when you set y2 equal to 0, it creates a horizontal line along the x-axis, or where the height, or where the height displacement generally is 0. So on my graph here, here's what it looks like. For me, I'm going to see a red line. For you, you're going to just see maybe potentially a x-axis and a curve that goes through it. It won't look any different, but here's what this allows us to do. We can do, instead of second trace or shift trace and x-intercept or 0, what we can do is we can go second trace, and we can go down to intersection or intersect. We can click on here. It will ask you, for me it says left bound, right bound, so I'm going to do left bound, right bound, and enter. For you, what it's going to do is it's going to say first curve, second curve, guess, or for my Casio users, it's just going to give you the solution when you use second trace intersection. For my TI users, when it does the first curve, second curve, guess, it's telling you to go blue curve, red line, which is the second curve, and then guess where they intersect. And so what I recommend is you go right over top of whatever intersection you're looking for and click enter one time, enter a second time, and enter a third time, and it will give you this solution. Now, to nobody's surprise for these ones, let's write out our instruction here before we tell our solutions. Second trace and intersection, or more importantly, intersect, as it says on the calculators. And then for my Casio users, you're going to click Shift, G-solve, and then intersect or INT. Perfect. Once we do this, our solutions are going to be the following. X is equal to negative 1.28 for the one x-intercept, and x is equal to 0.78 for our other solution. There we go. Perfect. So we got our two ways of doing this. We can either just do our zero method, which is fine, or we could do our intersection method. Either one is going to be totally fine. Don't overthink these. Don't think you have to use one or the other. Don't think that I'm going to trap you into doing one or the other. You just need to use the method that works best for you. I sometimes like the intersect method because the left and right bound stuff can be a little confusing sometimes, but I mean, like these are both going to give you the same solution. So you choose whatever you feel is best for you. All right, now here's where we go into our last section, and it's dealing with quadratic equations where they're real world scenarios where we have to type them in and then create a bit of a sketch for the graph and then talk about what certain piece of the context do we need, whether it be how far they land, maybe it's a sum of numbers and we need the two numbers, or it could be something talking about something economic like profit. Now, we've talked about all these examples in the previous unit, which was quadratic functions, and we talked about how you can complete the square to get maximum revenue or price or quantity. We talked about how you can complete the square to get like a maximum number that would be a result of two integers. We've also talked about area situations where we said, hey, if I want the area in the perimeter, or considering area and perimeter, what type of length and width would maximize the area, and what are those lengths and widths? This is no different. We're just going to solve these directly from our graphing calculator, but highly focus in on the x-intercepts. So instead of looking for like the maximum or minimum, now we're typically going to be looking for what is the x-intercept on these. Wait, let's read through the first one. A skateboarder jumps off a ledge at a skate park, and his path is modeled by the function of h of d, where h is the height above the ground and d is the horizontal distance, aka what we can do here, and I highly recommend you do this in your notes here, is the h value is technically the y, and then your d value is technically the x's here. All right, now what they want us to find is the following. In this case scenario, write a quadratic equation that represents the situation when the skateboarder lands on the ground. Okay, what we're going to do here is the following. So the equation can be written as the following. We could write this as h of 0, which is, and not h of 0, but we could write this as h of d, which is equal to 0, meaning when he lands on the ground, the height is 0. This is equal to the following function, negative 0.75. Let me make sure I put that in. Negative 0.75 d squared plus 0.9 d plus 1.5. Perfect, there we go. And I'm just going to move this a touch over just so that it doesn't intersect with our graph that we're eventually going to draw. Now, instead of h of d, what we could write this is something that we can type into our graphing calculator. So rather than it being h of d, I'm going to write this as y, which is equal to 0, which is equal to negative 0.75. And instead of d, I'm going to write x. This is x squared plus 0.9 x plus 1.5. This is something that we can type into the graphing calculator. But both mean the same thing, whether I'm talking about h of d or y, x's and y's, that's why we had them indicated above just as a output and an input, where our output is the height, his horizontal distance is the input. Okay, now let's type this into our graphing calculator and see if we can build out a window for this and then talk about how far he is, or the distance away that he lands to the nearest tenth of a meter, or to one decimal place. Now I'm going to bring my graphing calculator over to my other side here. We're going to click y equals. You can keep y2 as 0. This is actually fine because it allows us to do the intersect method we just talked about. What we're going to do is we're going to type in the function, which was this original function of negative 0.75, and instead of d, we're going to write x squared plus 0.9x, and not squared. I don't want to make that mistake. We're going to write x, and it looks like I forgot a sign in there, so I'm going to make sure I plus 0.9x, and then plus 1.5 on this side. Perfect. Okay, so we got our function. It's all in terms of x's, which is great. Now we're going to graph it. Now we look at this, and we want to be thinking about this in terms of real world application. When we look at this skateboarder is Yeah, I mean, maybe he could start at negative distance. That might be okay. But for the most part, when we look at this, we want to consider it as he's going to start at some sort of height, or he's going to be skating along. He's going to jump in the air. He's going to come back down. What they want is they say, at what distance from the base of the ledge will the skateboarder land? Well, the ledge in this case is actually at the y-intercept, or the y-intercept, because if he's on a ledge, he's not starting at ground level. So it would be inappropriate to keep our graph like this, where it's at -1 for the x, and then he jumps up in the air. This parabola would be okay if they said, hey, he starts on the ground, and then he does some sort of ollie, and then he goes in the air and lands back on the ground. But for this situation, we want to adjust our window so that he's starting at that y-intercept, or he's starting on the ledge and leaping off. So to do that, we're going to get rid of all the null space, or this stuff on the left-hand side we don't like for the x's. So instead of this, what I'm going to do is I'm going to make my x minimum. Let's make sure, whoops, I'm going to go back to my window. My x minimum, I'm going to clear that out and make it, let's say, negative 0.5. There we go. And I'm going to regraph this. And here we go. Here's a graph that maybe looks a touch better. We could even decrease our x's even more if we wanted. But what we're going to do is below this, let's actually just record our window settings so that everybody has it. X is equal to, in the window, we have negative 0.5 for x. We have a maximum of 2.5 and a scale of 1. Awesome. For our y's, we have a minimum of 2.5. We have a maximum of 2.5, and we have a scale of 1. All right, let's graph it again. And what we're going to do is we're going to try and get the information. In this case, that said, if he's up on the ledge, which is that y-intersect, and let's even just draw it out here so I can kind of talk about this as a rough sketch. So I'm going to go, let's create our Cartesian plane as such. We have a graph that kind of looks something like this, where it's like he's leaping from over here, and I'll use my pen tool there. He's leaping from over here. He kind of comes up, and then he crashes back down here, or he comes back down to the ground here. We're going to be looking for this x-intercept, where he starts at this position here. Now, we know from the previous portions that when we look at the general form equation, the c value is actually the y-intercept. So I'm going to write this right here as 0 for x and 1.5 for y, meaning this skateboarder starts 1.5 meters in the air because it's a result of that c value. And what I'm actually going to do is just highlight this and connect these two together. The c value is the y-intercept. Now we're looking for the x-intercept, right? Because it's how far he lands away, where our y-axis is h of d, or the height he's above the ground. This is the horizontal distance he's away from his original starting position. Now, let's do this in the graphing calculator. TI users, shift, trace. You can either do intersect if you have y2 equal to 0, or you can do your 0, which is the second one. I'm going to do 0. We're going to go to the left-hand side of that x-intercept, click enter. I'm going to click over to the right-hand side, click enter. For you, you're going to have to guess. For me, I'm able to just go directly to it here. Now, it looks like I'm getting an x-intercept of 2.3 for this situation. Now, for this one, we want to make sure we're getting an accurate solution. For this one, it's kind of giving us a range here, but I'm going to trust the one that's on the very bottom here, where we get roughly about that 2.06. Let's even just do another calculation just to see. Let's do second trace intersect, because it seems like it's giving me, for my calculator at least, it won't do this for yours, but for mine it was giving me a bit of an error. So I'm going to go left, right, in terms of the intersect. For you, you just have to click enter 3 times. It looks like our intersection point is going to be at 2.13, which means he lands about 2.1 away. So I'm going to put that away and then arrow to this and say that it is at 2.1 and 0 for y. And that is to the nearest tenth of a meter. Awesome. And then that, I think that's all we need to put here. Maybe we should put a sentence even. We'll just summarize that over here. So the skateboarder lands 2.1 meters away from the original position. There we go. And you could say even from the ledge, even that would be okay too. But I just say the original position because the ledge is the original position. Now we're just going to highlight this because this is exactly that key critical information we were looking for, and then we're done from there. Perfect. All right. And again, if they don't ask you to include the window settings, you don't necessarily have to, but just make sure that when you draw your sketch, it's an appropriate diagram that represents the overall parabolic shape for the situation. Realistically, I could have probably even got rid of some of this negative y space down here, but this shows the full graph in a nice picture, so that's also okay here. All right, let's go into example 2. This is going to seem very similar from quadratic functions or our first unit. Two numbers have the sum of 10 and a product of 24. Now, when we say sum of, they're going to add to. When we say product, it's multiply to. Now, what single variable quadratic equation can be used to represent the product of the two numbers, or when we multiply the two numbers together to get the 24? To do this, here's what we're going to do. First and foremost, they said that the sum of two numbers, which we're just going to generalize as x and y, is equal to 10. From here, they said the product of x and y was equal to 24. Now, our goal is to write this as a single variable equation, so what I'm actually going to do is to keep it in terms of x, I'm going to isolate for y in that first equation. So if step number 1 was getting out our equations, step number 2, I'm going to write this as y is equal to, and we're going to subtract the x from the left-hand side and move it over to the right. This is going to give us y is equal to 10 minus x. Now what I'm going to do is I'm going to substitute this into our equation for the product. So if we have x times the y value, which is 10 minus x, this is equal to 24. Now what I'm going to do is write this as 10x minus x squared is equal to 24. Now, I don't really like this as is because I have like x's on one side, and more importantly, I have even a negative x squared on the left-hand side and 24 over here. I'm going to take all of this and subtract it over to the other side. Now, when I subtract it over to the other side, let's even just write an arrow continuing up here. This is going to be the following. 0 is equal to x squared minus 10x, and then plus 24. There is the equation we can use here. So when they say write it as an equation, we now have it as an equation in terms of x. Now, if you isolate it for y instead, like we did in class, you can actually just flip them to being the x's, and this is totally fine. So there's our equation. All right, now we want to figure out the graph, or we want to determine the two numbers by graphing this. So we're going to bring out our graphing calculator again, go shift clear, or second clear, and then what we're going to do is you can keep the y2 as 0, so we can do our intersection method if you want. I'm going to type in the function of x squared minus 10x, and then plus 24. We're going to graph it. And again, it's maybe not going to show you the information that you need. So what we're going to do is we're going to go window, or zoom standard, and then this is going to be the graph. Now, we want to get rid of some of this null space or the white space. I don't like all those negative x's because look at how much white space is on the left here. So for the window settings, I'm going to decrease my x minimum to 0. Not 100, but 0. There we go. So this is the graph I get. And then I want to eliminate some of that white space on the bottom for the y's. So I'm going to lift the graph up by clicking window, and I'm going to make my y minimum something like -2. And when I make it -2, let's just copy out all these window settings here. So off to the side, on the low part, you could be like x, put our information in here. We're going to go 0 for the minimum, 10 for the maximum, 1 for the scale. For the y's, we're going to write it as our minimum, which is -2, our maximum, which is 10, and our scale, which is 1. Now, in this problem, they didn't ask us to record these, but in some written response problems, or some things you might be assessed on, they often love to ask you for the window settings just to make sure that you know what you're talking about and that you create an accurate window. Now we graph this, and here's what it gives us, a nice parabolic shape. Let's see if we can sketch this on our graph here. So I'm going to go over here and create my Cartesian plane. So based on where the lines are, it looks like the x-axis is here. We made our x value 0 for the minimum, so it's going to be right along the edge here. And then using our graph here, we're going to go down and make it look like this. So it was like this, it cuts below, comes back up, and there we go. Now, realistically, I want to make this a little lower, so I'm going to freehand this here. I don't want my tool to lift it up more than it has to. So there's our graph. And then when we sketch it, we just want to make sure our arrows are on the end because we know it extends to infinity and that it's not just cut off by the graph. There we go. Now we have two intercepts here. So one x-intercept is on the left-hand side here. The other x-intercept is over on the right-hand side here. And now what we can do is we can do our method of either second trace 0 or shift g solve 0, or we could do shift g solve intersect or second trace intercept. Either way. For our case, let's do second trace 0. Let's try it out. So we're going to go to the left, enter, to the right, enter, and then it's going to give us this value here. Now, for some reason, I think it's getting tripped up by the fact that there is a y equals 0 here. So I'm just going to clear this out just for a second so that when I actually do my second trace 0, it should give me a more accurate solution and not be confused with this piece, right? There we go. So we get a 0 at positive 4. Now, your graphing calculators wouldn't trip it up that way, but for mine, for some reason, it's being a little stubborn. So I'm just going to clear out that y equals, which allows us to do the intercept. So we get at 4 and 0. And then we're going to do our other one, second trace or shift g solve 0. I'm going to go a little bit left of the point, a little bit right of the point, and we get a 0 of x equals 6. So I'm going to arrow right here and then put 6 and 0. Awesome. And there we go. So we've appropriately labeled our graph. Now, realistically, what we could do is write them in terms of, we could write an x-axis here, because this is symbolic of x. This is symbolic of our y-axis or our output, but I mean, that's just secondary to this. Now, what we're going to do is they asked us for two particular things. They said, determine the two numbers by graphing the corresponding function. The two numbers are the x-intercepts. These are considered the roots, zeros, or solutions to the graph. So now what we're going to do is just write a sentence that describes this right in our, maybe we'll do it in the space right here below, because we did that in the previous problem. Therefore, the two numbers are, we have x is equal to 4, and we have y, which is equal to 6. Now, realistically, because in this case they're both x-intercepts, writing out x equals 4, y equals 6 might be a little bit confusing, but remember, it was in terms of these two numbers. And so we just used x and y to define the two numbers in very arbitrary terms here. So even though it's not technically a y value for 6, we just treat it as, well, these two numbers or the two solutions for this are going to be 4 and 6. So don't get confused with being like, oh, it's an actual y value for this one. And that's why I almost caution against this on the top side of the graph here, being like, that might be a little confusing if we write in y equals, because then you're basically saying that we should have some sort of y equals 6. Don't confuse it that way. We're just talking about two arbitrary numbers where x equals 4, y equals 6. If we wanted to actually confirm this is true, let's just do this for a second. So we have x equals 4, y equals 6. If I had 4 and 6 together, that equals 10. Okay, so check mark. If I take 4 times 6, that gives me 24. Check mark. So if they ever ask you to verify these solutions, to verify them, we can put them in the equations. I can even do this below here. 4 plus 6 is equal to 10. Check mark. There we go. Verified. We can write this as 4 multiplied by 6. Is this equal to 24? Yes, it is. This is also a verified solution. So in math, we like to sometimes ask, oh, can you verify these things and make sure they're okay? Yes, we can. We can plug in those two numbers. All right, there we go. Let's highlight it, make sure that this solution is known. I'll even highlight the verification because I think that's also important here. All right, now we're at our final problem, which is dealing with a revenue problem or a profit margin. So this is more of an economics problem. I love economics, like I've said before. So this is right up my alley in terms of content. The profit can be modeled by Pn, where n is the number of sales they make and P is the profit, and we have this equation to represent this. Now, in this situation, this business hits a break-even point when the profits are equal to 0 or when P equals 0. The business is neither making profit or losing money. That's hence what breaking even is. You're paying your employees, you're selling enough product to then cover the costs of maybe the rent and your employees and all that stuff, but the owner isn't making money. They're not taking anything home to their own bank account. Now, if the profits are 0, at what point does this occur? So if I was to sketch this on a curve, where is the profit 0? This is another way of saying, where's the y value equal to 0? And they want to determine how many sales this is. So just to make this a little more obvious for us here, what we're going to do is the following. We're going to write out the equation of Pn is equal to, and I'm going to just basically rewrite it exactly how it is, 0.1n squared. I'm going to write plus 100n, and then minus 21,000. Okay, I'm going to rewrite this in the following way. Instead of Pn, I'm going to write this as y. I'm going to write this as going to be equal to negative 0.1 x squared plus 100x, which is minus 21,000. There's just a constant term, no problem. And this is all going to be equal to 0. Remember, because if we have an output of 0, and I'm even going to maybe put that over on this side here. They told us, where's the profit equal to 0? I'm going to sub in 0 for the Pn, representing that they make 0 profit. When this equation hits 0, what are those two values? Or what are those x values? What are those input n values that help us solve this? So let's bring out our calculator here, and we're going to solve this. Forget if it was on my left or right. Okay, there we go. We're going to clear out this. So clear out that original function and type in negative 0.1 x squared plus 100x, and then minus 21,000. Graph. Okay, this one's going to be a little difficult because we're going to go zoom and zoom standard, and we're still not going to be able to see it. What we have to do is we have to play around with a couple things here. And I want you to think about what's actually happening in reality on this situation. You have a profit where, remember what this negative 21,000 actually represents that's on this backside here. Negative 21,000 is the y-intercept, or in this case, the p-intercept. It's the profit intercept. So what this means is that when they haven't sold any units, when this is all canceled out, when they have not sold a single unit, they're technically $21,000 in debt. And that could be from opening up the shop and having to buy the supplies and rent the space. They're negative $21,000 in the hole. Now, they need to sell a certain amount of product or have a certain amount of ends that would increase this such that this $21,000 is offset and that we could eventually get to this 0 profit. Because right now they're at negative 21,000 profit when they start. What we want to do is get it to the point where this portion equals this portion such that it becomes 0. So now what we're going to do is we're going to adjust our window settings the following way. Our minimum for the y, we're going to set this down to negative 22,000. So it's below that original starting point. We're going to set our x maximum. Well, if they're in the whole $22,000, to make profit, they're going to have to be somewhere around like at least 10,000. So I'm going to click enter and see what we get. All right, now this is the graph we get. It's very flat, and you're like, okay, well, this doesn't really show us much. So what we're going to do is we're going to go window, and now we have to deal with our x's. In terms of x minimum, we're not going to sell negative product, because remember, at the end of the day, if I look at my n's and my x's, what these actually mean is the number of products. So you're not going to sell negative 10 units unless people are returning product that was never sold in the first place. That wouldn't make sense. So what we're going to do is say, let's set our x minimum to 0 instead, because they're going to start at 0 products that they've sold. N or x could be 0. When these are 0, it means that they start in basically debt. They start where 0 products are sold. They've had to purchase a bunch of stuff to start the store. It's negative 21,000. Now, for the X max, we're going to hope that they can sell even 1,000 units would be great, because they need to sell a ton of their products, whether it be water bottles or whatever else it might be. This business needs to start selling product and in large volume in order to break even. So we're going to graph this, and here's what it's going to give us, this following graph. Now, I want to copy out these window settings with you, because for some of you, you might have missed that and made sure that you don't have it yet. So let's go off to the side here, and we're just going to write it over in the margin point here. So let's bring out the graphing calculator again, shuffle over. Okay, I'm going to start with my x's. X, the minimum is 0 products. The maximum, we're set it to about 1,000 products. And then the scale factor was 1, just like we've had before. The y, this could be, our minimum was negative 22,000 because we wanted to be below what we originally started at to open the store. The maximum we set to 10,000 because we're like, hopefully they can earn about $10,000 eventually, or maybe around that. And then the scale factor was just 1. Now, for some of you, again, you're like, why do we keep the scale factor as 1? I mean, you could change it if you wanted to, but it's just one more thing you have to adjust. And I mean, when the numbers are in the thousands like this, it might make sense to do some sort of scale factor, but I think for now, just keeping it as 1 simplifies our job, and we just have to deal with our mins and maxes. Now, to each your own. You might have a different way of thinking about this, but I like this model of it. Now we graph this, and what we're going to do is we're just going to roughly sketch out this exact same situation. So I'm going to move my graphing calculator over here, and then I'm going to create my axis points, or maybe it makes more sense to have it over here. So I look at this and I say, well, my x-axis is somewhere towards the top. My y-axis was exactly right on the left because we said it starts where x equals 0. And now what we want to do is just sketch out this curve. So I'm going to bring this over here and then just take one more look at it. It's at negative 20,000, cuts through up here. So it's like this, and then it swoops, and then it comes back down like this. Perfect. Okay, this graph actually does pretty well with the auto sketcher tool, so I'm going to keep it like that. Excellent. And then we want to make sure we have our arrows on it representing that it extends to infinity. Now, not the best sketch of it, but it will do. Now, what we're going to do is we're going to put a dot here and a dot here, and in this problem, it definitely makes sense to label our axis. I'm going to label this as N. This is going to be our PN, or our profit. Okay, we need to remember what this is doing in all reality. The PN, or our vertical axis, is the profit the store makes. The N is the number of units they have to sell to achieve a certain profit. What this means is the following. Anywhere down here or down here, the store is losing money. Their profit is negative because it's below the x-axis. This is all the negative profit margin. So if they sell anywhere less than this amount of units, they're all in the negatives. If they sell any more units than this, they're in the negatives, meaning you can actually sell too much product and then it's like, okay, well, you have maybe too many things in the store. You have too many SKUs. Where they want to aim to be is right in this sweet spot. And more particularly in this question, they actually asked, where did they break even, or where is that profit margin exactly 0, which is right along the x-axis. This is P equals 0. If we wanted to write this, we could actually do this in our notes here. I'm going to write this as the following. This is Pn equal to 0, right along this line here. I'm going to put a comma there just to show that this is what's happening. So in our calculators, the break-even points are those two x-intercepts, or in this case, the two n-intercepts. To solve this, we're going to go second trace 0. For some of you, we can even do the intercept method, but to do the intercept method, you want to have y2 equal to 0. So maybe let's try that for this problem. Set y2 to 0, and we're going to do method 2, which is the intercept method. We see that a line is drawn in red. That's the horizontal line along Pn equals 0. We see our graph cut between this. You're going to go second trace. We're going to go down to intersect. We're going to go left bound, right bound. In your calculator, for the TI users, you're going to go right on top of the point and go enter 3 times. For my Casio users, you're going to go shift G solve INT, or intercept, and it will give you the values and you can just arrow between them. It's really nice. The one intersection point here, or the 1, 0, is going to be at 300 and 0. Okay, so we get 300, which is the first profit margin here. And then let's make sure we write this out here. So I'm going to arrow over here, and I'm just going to do them above. So it's 300 products is 0 profit. Now I'm going to arrow to this one so that we can set up our next bracket here. When we do second trace and we do our intersection is going to be left. And again, yours is a little different than mine, right? Okay, we get an intersection point at 700. So 700 products and 0 profit. Now, just to confirm our answer, I'm going to go back to y equals, clear out the y2 equals 0, and go second trace 0. And I'm going to do the 0 method just to confirm that this is actually the x-intercepts. There we go. Yes, we get 300 for our first one. Second trace, 0. I go left bound, right bound, and enter. I get 700. So great. This is our function for this. And these are our x-intercepts. Now, to provide some contextual information to this, these are the 2 points in which the store will break even. They sell 300 products. They end up making 0 money. If they sell 700 products, they make 0 money. So to maximize profit, which comes from our previous unit, they might have to be somewhere between here. But that's not the point of this unit right now. Right now, we don't want to be considering max or minimum profit like we did with completing the square. Right now, we want to deal with what would be the break even, or the bare minimum products they have to sell. What would be the maximum amount of products they have to sell in order to break even in both directions. Okay, determine how many sales the company needs to reach this break even point. Let's just formalize it below here. They need 300 or 700 sales. There we go. Okay, and then we'll put a period there. Realistically, I can make that sentence more detailed, but I kind of ran out of space. They need 300 or 700 sales to break even. What conclusion could the business owner make from the solutions to this quadratic equation? Well, I'm going to write it in the exact way I said it. Essentially, the following has to happen. The store must sell between 300 and 700 units of product in order to not lose money. Perfect. So this is our number one conclusion here, is that the store has to be between. And graphically, I mean, this is completely justified. When we look at the graph again, what we see is that if they sell any less than 300, they're over here. This is a no-go zone. This is where they lose money. Same thing if they sell greater than 700, it's like, oh no, then they're in the opposite side where they're also going to start losing money. So to be profitable, they kind of have to be somewhere in about here, or else they're spending way too much of their capital either paying employees and not selling enough, or they're paying too many employees and buying too much overhead, and then that's leading them to have negative profit. Now, again, we're not an economics class, so I'm not going to go into this and be like, can you do a research study on this? No, it's not going to be what we're doing. But what we want to do is just to provide that basic context of, if profit is positive, it means that we have to be between those certain units. So our domain and range in this case, for the appropriate domain and range, would be a domain where it's between these two x-intercepts, and a range which peaks here and only goes as low as zero profit. We wouldn't want to have anything below here, or else what it would do is cause us to be in negative profit. Okay, here's where you're going to go to your assignment. Your assignment questions are in the bottom here. Go to the textbook, complete these problems. I guarantee you need practice on these ones, especially when it comes to adjusting your window settings and working with the graphing calculator. If you don't make an effort to do this, it's going to become extremely difficult, and you don't want to get stumped as you're working on these problems. And in fact, I will have a show for this when we get to class. So I want you to practice this, see if you can do these graphing calculator situations on your own, and see if you can answer the questions based on these. All right, good luck with your practice.